Hello, everyone. This is Xiaowei. I just graduated from the University of Minnesota last month from Vipin's group and joined the University of Pittsburgh as assistant professor in computer science. So very happy to have this chance to give this talk in our HDR kgml workshop. And my talk today is about integrating physics into machine learning for monitoring scientific systems. So in these recent years, we have seen this machine learning and data mining, these techniques have found a lot of success in different commercial applications, like in computer vision, natural language processing, and so on. So that's why there's a growing interest in using these machine learning techniques in scientific domains as well. But actually, we have seen many failure examples for directly applying these machine learning techniques as black box in these scientific problems. For example, the very famous Google flu trend prediction. And also in the domain of climate and biochemistry, there are many failure examples. So we may want to ask, why do these black box machine learning methods fail in our scientific problems? And here we summarize a few major reasons. The first one is usually these scientific problems, they are very complex, so they involve a large number of physical variables, and the relationship between these variables are non-stationary, so that means the relationship can change over space and over time. It's very hard for machine learning models to capture such kind of complex relationship solely from data, and especially if we have access to only very limited amount of observation data. So that makes the training process even more challenging. And also, most existing machine learning models, they focus on mining the statistical relationship from our available observation data. So they are not aware of the underlying physical processes. So in that case, it's possible that these machine learning models can produce some results that are inconsistent to our known physical relationships. For example, they may not conserve energy or may not conserve mass. And that's why these many domain scientists, they may not fully trust these kind of black box machine learning methods. And also, they can only discover the relationship from our available training data. So it's very likely that these learned patterns from available training data may not generalize to scenarios that look very different with our training data. So traditionally in scientific domains, the domain scientists commonly build different types of physics-based models. And these physics-based models are mostly developed using our current knowledge of the scientific theory. But there are also several well-known limitations of these physics-based models. For example, their representation of physics is usually incomplete, either because some physical processes are still not fully understood by domain scientists, or they're just too complex to be directly modeled. And also calibrating these physics-based models can also be very time-consuming. And on the other hand, machine learning models, we know they're very powerful and they can automatically extract different types of complex relationship automatically from data. But training such kind of machine learning models usually require a large amount of labeled data. And also, as we mentioned, they can produce some results that are inconsistent to our known physical relationships. And that's why we want to combine these two types of models together, and we call this hybrid framework as physics-guided machine learning. And the idea here is that we want to leverage both the power of machine learning and also the physical knowledge encoded by existing physics-based models. And this kind of hybrid framework actually can be widely applied to many different domains because so far in these scientific domains, people are still heavily relying on different types of physics-based models. And there's still a large gap for using these physics-based models to simulate true phenomenon. That means there's still a lot of space to make improvement. And my talk today is going to be focused on using this hybrid framework, physics-guided machine learning, for modeling physical systems with interacting processes. And I want to use the example of predicting water temperature and stream flow in river networks. And this study is very important because an accurate prediction of in river networks actually can provide many useful insights about the like aquatic ecosystems and the water quality and so on. And in these river networks, there can be multiple river segments. So they can have quite different dynamic patterns because they have different geometric structure and also they have different climate conditions. But these different river segments, they can also frequently interact with each other. So like the water abstracted from upstreams can directly impact the water downstream. And the most challenging part is that usually in a river network, there are only a few river segments that are frequently monitored. So that means we usually have limited training data for training advanced type of machine learning models. And so from a machine learning perspective, here we list 3 major challenges involved in this project. And then we also provide our solution for each one of them. So the first challenge is that, as we mentioned, like most river segments are poorly observed, or they are completely unobserved. So in this way, it's impossible for us to build individual machine learning or purely data-driven models for each river segment separately. And so that's why we will, in this work, we will build a global machine learning model for the entire river network or the entire system. And the second challenge is traditional machine learning models cannot simultaneously capture the interactions between different processes or between different river segments, and at the same time capture the temporal dynamics within each process. And to solve this problem, we will propose a new machine learning architecture called recurrent graph neural net. And the last challenge is that we know that the power of these deep learning models or these neural network models mainly comes from their ability to extract these hidden representation or hidden variables in these middle layers. But these learned or extracted hidden variables can become less meaningful if we only train this model using limited observation data. So to solve this problem, we will propose a new learning strategy. Basically, we want to transfer the knowledge from existing physics-based models to guide the learning of this hidden variable or hidden representation. And we will cover these challenges and our solutions one by one. So we start with introducing the basic structure of the recurrent neural net. So this type of machine learning model is very widely used in different machine learning applications. And the power of this model mainly comes from their use of this RSTM cell or the long short-term memory cells which can be used as memory to preserve all the information from the past history. And as we mentioned, like in our work, many river segments are poorly observed. So we cannot build individual models, so that we will build a global machine learning model for the entire river networks. So here, for example, we consider this very small river networks with 3 different river segments, A, B, and I. So in this case, the global machine learning model or the global recurrent neural network model means we train this global recurrent neural net using all the available data set, all the available observation data from all these 3 river segments. So we combine the available observations from the 3 river segments together to train this recurrent neural nets. And after we train this model, we can apply the model to each river segment to generate predictions, the meaning of global machine learning model. But as we mentioned, like this recurrent neural network can capture this temporal dynamics, but it cannot model the interactions between different river segments. Like in this case, it cannot capture the influence from upstream A and B to the downstream segment I. So that's why we propose this new architecture called recurrent graph neural nets, where we introduce a graph structure for this to represent these different river segments in this network. So here in this graph, each node represents a river segment in this network. And we add an edge for between each segment I to segment J if segment I is upstream of segment J. And the weight or the affinity level between each pair of river segments is measured by their stream distance between this pair of river segments. And remember, this is the structure of the recurrent neural nets. And for example, here if we wanna model this downstream segment I, so we also want to incorporate the influence from its upstream segment A and segment B. So what we do is when we calculate the RSTM cell for the downstream segment I, we also incorporate some hidden states or hidden variables HA and HB from upstreams. So basically from HA and HB, we first transform it into QA and QB. Then we pass this information from QA and QB to the RSTM cell structure at downstream segment I. So that when we calculate this RSTM cell, we can gather sufficient information. Basically, we can gather or receive the influence from its upstream segment A and segment B. But now that we propose this structure, but these hidden variables, they are automatically learned if we directly train this machine learning model using an end-to-end fashion from observation data. So we don't exactly know what kind of information is propagated from upstream to downstream segments. And then if we train this model directly using very limited and less representative training data, it's very likely that these hidden variables QA and QB can become less meaningful. So to solve this problem, we propose to transfer the knowledge from physics-based models to guide the learning of these hidden variables so that we can enforce some very general physical relationship amongst different river segments. So we will use an example of modeling the water temperature in river networks. So, so according to the energy conservation law, for each river segment, the temperature change is dependent on the difference between incoming and outgoing energy fluxes, and plus an additional term of net heat advected from upstream to downstream segments. So basically this term HADV, this net heat advected, this term is the influence from upstream to downstream segments, and it's the value that we want to model in our graph neural nets. And this term HADV can be calculated as a function of a set of intermediate physical variables. So these include like the stream flow, like the water temperature of the upstream segments. And actually, this is very intuitive because we can imagine like when the water merge from upstream to downstream segments, then the amount of water that flow into the downstream segments and also its water temperature can directly impact the change of water temperature at downstream segments. And to model this relationship, we propose a new loss function. Basically, this loss function is used to ensure or guarantee that we can extract this set of intermediate physical variables from our hidden variables QA and QB. So here we represent these intermediate physical variables using the symbol SA and SB. And then by minimizing this loss function, we can guarantee that we can extract this SA and SB from our previous hidden variables QA and QB. So if we can do this, then we can make sure that these hidden variables QA and QB, they indeed contain sufficient information to represent these intermediate physical variables. And then once they are passed, once these hidden variables are passed to the downstream segment, this LSTM cell, then this LSTM cell can gather sufficient information to estimate this term HADV, which is basically the impact from upstream to downstream segments. And in our implementation, this set of intermediate physical variables can be simulated by running a physics-based model. And then we notice that the calculation of this loss function is totally independent of true observations. So that means we can minimize this loss function in a separate pre-training stage. So basically the pre-training is to update these weight parameters along these red color connections. And then once we finish pre-training this model structure, we can just fine tune it using limited amount of true observation data. And here we show some results for modeling water temperature and stream flow in a river network. So this is in Delaware River Basin, but it's a subset with a total of 42 different river segments. And our training data are selected from this 24-year period from 1980 to 2004, and we test in the following 12 years. And so here, these numbers are prediction RMSE, so the lower the better. And we can see that our method, the last two rows are our proposed method. RGIN basically is a recurrent graph neural net, and the last row is the method after using the knowledge transfer or the pre-training. And we can see our proposed method always gives us a better performance compared with baselines, and that's because we use this kind of graph structure to model the interactions between different river segments. And we also trying to randomly remove some training data. Basically, we randomly select 0.1% of data or 2% of data, basically to evaluate the performance of each method to see whether it can still get a good performance even with access to a very limited amount of training data. And we can see all these methods get worse performance when we reduce the training data. But our method can still get a reasonable performance even with just 0.1% of training data. And the reason is because we do the pre-training using large amount of simulation data, because we can always generate simulation data for every single date and for every river segments. So after pre-train the model using a large number of simulation data, then we can get a good initialized point for this machine learning model, and then it can be fine-tuned using very few amount of true observation data. And here we show the distribution of prediction error across different river segments in this river networks. And here we show the left side is our proposed recurrent graph neural net, and the right side is the standard recurrent neural net. And here the darker blue color means the better performance, and the darker red color means worse performance. So in general, we can see for most river segments, we have a little bit darker color, darker blue color. That means we get better performance. And especially for certain river segments, we can see our method get much better performance. For example, this segment in this dashed circle. And the reason is because in this segment, we have very limited amount of training data. So in the first 24 years, but we have plentiful of the testing data. And the performance is bad in RNN because if we don't have sufficient training data for this segment, then it cannot capture the local patterns of this river segment. But for our method, even if we don't have training data on this segment, but we can still use this information propagated from its neighbors in the graph. So we can still learn something useful to help improve our prediction on this river segment. And to better verify this assumption, we do this following task. Basically, we select 5 river segments in our river network where we have sufficient training data for both temperature and stream flow. And then we intentionally hide the training data for either temperature or stream flow. And then we measure the performance before and after we remove such training data. So here we show the performance before and after we remove the training data. And in the middle, we show the increase of prediction error after we remove the data. And we can see that our proposed method always gives us the lowest increase of RMSE after we remove the data. So that means our method can still be effective even for modeling those river segments that are completely unobserved. And finally, we do the generalization test. Basically, the idea is that we want to train and test the model using data from different distribution. So for example, like for water temperature, we will train the model using data only from colder seasons, and then we test in summer. And for stream flow, we will train the model using data only from those high flow streams, and then we test on data from low flow streams. So the second column here is basically the baseline, and we show this generalization performance in the first column. So we can see like some methods like ANN, the standard neural net, and the standard recurrent neural net can give us rather high performance in this generalization test. That means this method, the learned patterns from this high flow cannot generalize to low flow streams at all. But our method, the last row, after we do the knowledge transfer through pre-training, can always give us the lowest, much lower prediction error. And the reason is because after we do this, by doing this knowledge transfer from existing physics-based models, we actually enforce our machine learning model to learn some general physical relationship that always hold in different scenarios. And that's why it can be better generalized to different scenarios. And to conclude this talk, we propose a new model architecture, and also we propose a new pre-training strategy to transfer knowledge from existing physics-based models. And we have shown this method is quite effective for modeling river networks. And in future, we would like to pursue several interesting directions. For example, we want to further extend the current framework to see whether we can quantify the uncertainty level of machine learning models, so we know that, like, in what kind of situation can machine learning be better used to replace existing physics-based models. And maybe for some other special situations, the physics-based models is quite robust, so we can still keep using original physics-based models. And also, we want to provide some theories to see if we can identify the limitations of existing physics-based and machine learning-based models. And that's all for my talk. Thank you. Any questions?
Thanks, Xiaowei. Yeah, so there's a few questions for you. So the first one is, how do you guess how many hidden variables there are?
Yeah, so I think, so for my test, like what I do is I first implement this method using purely simulation data. So the simulation data is available on every single data, every segment. So on the simulation data, I try to tune those hyperparameters, and then I fix it, and then I use the same setting on the real true observations.
Next question, the physics model for heat transfer shown is missing exchange with the atmosphere in the stream bed. Are those terms really missing from the model?
let me share my screen. Okay. Right. So I think so. Just confirm that I understood the question correctly. So you mean the in this equation I ignore the some physical terms and whether that's included in my machine learning model. Is that right?
I think so. Yeah. If there's exchange with the atmosphere, heat transfer with the atmosphere and heat transfer with the stream bed.
Yeah, I think so I think we ignore several minor terms in this equation, but I think for the first term is basically like the input, the incoming energy fluxes, like the solar radiation and these things, and outgoing is like evaporation and these things. And the third one is the influence from the or the advected heat from the upstreams. But we ignore some minor terms, and we just found it's not. The performance won't change too much by ignoring those minor terms in this equation.
All right, I'll try and do two more questions quickly. One is, how do you define the river segments?
Okay. Yeah, I think I get this data set from our collaborators. So I think they have their way to segment this river into different segments based on their length and certain parameters. I'm not fully familiar with that process, but I can provide more details later.
And this is the USGS.
Right.
Yeah. All right, last question. How scalable is this approach? PRMRS SN temp models do not exist everywhere and they are expensive to build.
Right. So I think running these models can be very time consuming, especially like if we want to calibrate these models, it can be even, it just takes weeks of time. So what we do is, I think, so we're trying to, like here, so here is where we use the simulation from this PRMS as intent model. So we don't calibrate this model. We just use a like generic version of this model to generate simulations. So our assumption is that even if the simulations are not perfect for these river segments or for these river networks, but still by training from these simulations from a generic model, we can still learn some useful patterns. I think if we just do the predictions or just do the simulation using a generic model, that should be fine. But if we want to calibrate the model to make it customized to each river segment, to each river networks, then it takes a lot of time, according to my knowledge about this model.